Welcome back to the deep dive. Today, we are strapping into the driver's seat of what might be the most intense engineering challenge out there for students. Formula Student Electric, or FSE.
It really is. This is where the next generation of EV engineers gets forged in fire.
And we're going deep on the architecture of reliability. Because as a strategic powertrain architect, you're here to tell us it's not just about speed.
Not anymore. Our mission today is to apply a really rigorous professional engineering strategy. We're essentially creating the definitive statement of requirements, an SOR, for a brand new FSE team.
And we're focused on the core power electronics.
Exactly. The high voltage, or HEV, power systems.
Yeah.
The power distribution unit, the PDU, the DC-DC converter, and the onboard charger, the OBC.
When you think about Formula Steering, with these legendary teams like AMZ Racing or Green Team Stuttgart, your mind immediately goes to max power, max torque, that crazy 0 to 100 kph time.
And that's the classic assumption. It's also, for a new team, a fatal one. We've analyzed the long-term results, not just the flashy sprint times, and the data is clear.
What does it show?
Winning is no longer just about who has the biggest power budget. That's almost become a commodity. The real competitive edge now, the key to winning the whole event, is in 3 other areas.
Okay, what are they?
Flawless system reliability, first and foremost. Then maximizing energy efficiency. And third, maybe most important, is the absolute certainty of passing scrutineering.
Scrutineering is the big gatekeeper, isn't it? If you don't pass, you don't race. And you shared a really stunning statistic about that.
The numbers are brutal, and they really shape our entire strategy. We see over 40% of new EV teams fail scrutineering in their very first year.
40%.
They've built these incredible, powerful cars, but they fail on the fundamentals of compliance and safety. And most of those failures trace right back to the power electronics we're talking about today. Things like HV safety interlocks, insulation monitoring, just basic wiring mistakes.
So our mission today isn't to design the fastest car on paper. It's to design the car that is most guaranteed to actually finish the event and score points.
Precisely. This is the begin with the end in mind strategy. The ultimate goal is completing that 22-kilometer endurance event. That's where the big points are. And these 3 subsystems, PDU, DC-DC, OBC, they are the critical bridge between the HV battery and all the low-voltage controls. If that bridge fails, you're done.
Okay, so before we dive into the specific hardware, let's lay out the guiding principles, the 3 non-negotiable commandments that will govern every choice we make.
Absolutely. First, and above all else, safety first. This means a fail-safe design.
Yeah.
Total, non-negotiable compliance with every FSE rule, especially the ones for the high-voltage interlock loop, the HVIL, and the insulation monitoring device, or IMD.
And fail-safe means it always defaults to a safe state, right?
Always. If you lose power, lose communication, detect a fault, the system must instantly revert to a safe, de-energized state.
That's the foundation. What's the second principle? I hear this one might be a little controversial for students.
It can be. It's reliability over innovation. For the core safety components, the things that make the car go and stop safely, we mandate COTs, commercial off-the-shelf components from proven suppliers.
So no developing your own high-voltage contactors or IMD devices from scratch?
Absolutely not. You concentrate your innovation on system integration, thermal management, software areas where you can build real, lasting competence. You don't reinvent certified hardware.
That must be a bitter pill for engineering students who are, eager to build everything themselves.
It's professional realism.
Yeah.
Time is your most valuable resource in FSE. And betting an entire year on developing a component that a company like Bender or Gigavac has already perfected and certified, it's just a strategic mistake. COTS gives you a baseline of reliability you desperately need.
Got it. And the third principle?
Design for testability and maintainability. Scrutineering is a pressure test. So we have to design the whole system with clear labels, accessible test points, simple status LEDs. When the scrutineer asks, show me how you know the discharge circuit works, you need a test point and a voltmeter, not a deep dive into a software log.
Clear diagnostics save you time and stress.
And they dramatically increase your probability of passing.
That sets the table perfectly. Let's move to section 1, the non-negotiable foundation. You've called this regulatory compliance and isolation, and you said the rules are written in blood.
They really are. The key FSE electrical safety rules, EV.4, EV.5, EV.6, they're the result of learning from tragic industry accidents. They exist to prevent 3 things: electric shock, fire, and loss of control. Compliance isn't a suggestion, it's the price of entry.
Architecturally, we're dealing with 2 completely separate electrical worlds in the car.
Correct. We mandate the standard approach. You have a 400 to 600 volt high voltage system. This is called the tractive system, or TS. And separately, you have a 12 or 24 volt low voltage system, the GLV, which is grounded to the chassis.
And the core principle connecting them
Is absolute galvanic isolation.
Okay, how absolute are we talking here? What needs to be isolated from what?
Everything. Every single component that carries tractive system voltage, the battery cells, the bus bars in the PDU, the inverter, the high side of the IMD, all of it must be galvanically isolated from the chassis ground and the entire GLV system.
And there's a specific number for that, isn't there?
There is. The rule says the insulation resistance must be greater than 500 ohms per volt. So for our 600-volt system, that means we need to guarantee a resistance of at least 300 kilo ohms between any HV line and the chassis at all times.
300,000 ohms. That has huge implications for how you physically design the circuit boards, especially where high and low voltage have to interact.
It does. And this is where new teams often fail. Our SOR has to include an explicit PCB design mandate. You are strictly prohibited from running unisolated HV and LV traces on the same circuit board.
But what if you need to send a signal across that boundary, like from the low voltage VCU to control something in the high voltage PDU?
Then you must use specialized isolation components. We mandate the use of high-quality optocouplers or digital isolators with a minimum safety rating of 2.5 kilovolts.
So a dedicated chip that passes the signal using light or a magnetic field, not electricity.
Exactly. And the physical separation on the board is just as important. Teams have to reference standards like IPC 2221B to calculate creepage and clearance distances.
Creepage being distance along the surface, clearance is through the air.
Correct. And here's the strategic detail. We specify a 2x safety margin on whatever the standard requires. The standard is for a clean lab. The 2x margin is for a race car that's vibrating, heating up, and driving through puddles.
So we're not just designing to pass on a good day, we're designing for the worst day.
That's the only way to guarantee reliability. Now, let's talk about the most critical compliance device, the insulation monitoring device, the IMD.
The watchdog. What's the mandate here, and what's its hidden weakness?
We mandate the Bender ISO 165C, or an equivalent with a proven FSAE track record. The issue isn't the device itself, it's what it does when you first turn it on.
The power-up sequence.
Yes, it runs a complex self-check that can take several seconds. And during that check, it can momentarily output a false fault signal.
And if the main shutdown circuit sees any fault from the IMD, it latches and the car won't start.
Exactly. You get a car that can't power up reliably. It's a classic rookie mistake. So the SRR must demand a specific function in the control logic, power up masking.
So you're telling the system to ignore the IMD for a few seconds right at startup?
Precisely. The control unit has to be smart enough to ignore the IMD's fault output for a defined window, say, the self-check time, plus a 2-second buffer. After that, it monitors the signal continuously. It's a nuanced piece of logic, but it's absolutely essential for a car that works every single time.
Okay, that's a brilliant practical detail. Now let's talk about another one. The infamous rain test surprise. We're making our enclosures IP67 rated, which should be waterproof. But that's not enough.
This is a fantastic lesson in applied thermodynamics. IT67 protects against immersion, sure. But during the rain test, your DC-DC and PDU are running hot. Then cold water gets sprayed on the enclosure. What happens to the air inside?
It cools down rapidly and contracts. It creates a vacuum.
A negative pressure. And even the best seals are designed to keep pressure out. That sudden vacuum will actively suck water vapor, sometimes even liquid, right past the seals and into your high-voltage electronics.
And your insulation resistance plummets, the IMD trips, and you fail the test.
Guaranteed failure. The strategic solution isn't a better seal, it's pressure equalization. The SOR must mandate that all HV enclosures include a breather vent, like a Gore vent.
So it's a membrane that lets air pass through to equalize pressure but blocks liquid water.
Exactly. It prevents the vacuum from forming in the first place. It's a tiny, cheap component that makes the difference between passing and failing.
Incredible. Okay, last one for this section. The discharge circuit rule. The 5-second barrier.
The rules mandate that whenever the tractive system is deactivated, the main DC link voltage must drop below 60 volts within 5 seconds. Those big capacitors hold a lot of energy.
And just letting them bleed off naturally is too slow.
Almost always. So we need an active discharge circuit. And the key here is making it fail-safe.
How does it do that?
We mandate the use of a normally closed, or NC, relay. Its default state, with no power applied is closed.
Ah, I see. So during normal driving, you're actively powering the relay to hold the discharge path open?
Correct. The moment the shutdown circuit opens, it cuts power to that relay coil. The relay snaps back to its default closed state and instantly dumps the capacitor energy through a bank of power resistors.
So even if the entire low voltage system dies, the discharge circuit activates automatically.
That's the definition of failsafe.
Mhm.
And we still include high-value passive resistors, but only as a secondary redundant backup.
Yeah.
The active circuit is the primary safety system.
Let's move to section 2, the PDU, the power distribution unit, the heart of the HV system. You're recommending it be physically integrated with the accumulator. Why?
It's all about mitigating risk and complexity. Every inch of external high-voltage cable is a potential point of failure. It adds resistance, generates heat, and is a massive source of electromagnetic interference, or EMI.
So by keeping the PDU right next to the battery, you minimize the length of those big orange cables.
Exactly. It simplifies your safety analysis, improves efficiency, and makes the whole system much cleaner from an EMC perspective.
Okay, inside the PDU is the pre-charge circuit.
Yeah.
You said this is a huge failure point. Let's walk through the sequence of events that has to happen.
And logic has to be in check. Step 1. Close the small pre-charge relay, which connects the battery to the inverter capacitors through a big resistor.
To slowly charge them up.
Right. Step 2. You
Right.
monitor the voltage on those capacitors. Step 3. When that voltage hits about 90 to 95% of the main battery voltage, then and only then do you close the main contactors, the RRs.
And the final step.
Open the pre-charge relay to get it out of the circuit. If you skip this, you either weld your main contactors shut from the current surge, or you literally explode the capacitors.
You mentioned it's an energy problem. Can you walk us through the calculation for selecting that resistor?
This is where teams get it wrong. They think about power, but it's about energy. The formula is E equals 1/2 CV squared.
Energy equals 1/2 capacitance times voltage squared.
So let's take a common example. Big inverter system, 2,000 microfarads of capacitance at 600 volts. You run the numbers, that's 360 joules of stored energy.
360 joules. That's a huge blast of energy to dump through a resistor instantly.
It is. A standard resistor rated for, say, 50 watts of continuous power will just vaporize. It's not designed for that pulse.
So what kind of resistor do we need?
You need components specifically rated for high pulse energy. We mandate robust things like wire-wound resistors, thick film, or specific ceramic pre-charge resistors, and our SRR must explicitly prohibit the use of cheap carbon film resistors. They will fail 100% of the time.
And the actual resistance value, say in ohms, is a trade-off, isn't it?
It's the classic engineering trade-off. A high resistance, like 500 ohms, gives you a very low, gentle pre-charge current, but it takes longer. A low resistance, maybe 100 ohms, is much faster, but the peak current is higher.
So where do we land strategically?
We targeted total pre-charge time between half a second and 2 seconds. That's fast enough to not cause issues with the VCU startup, but slow enough to keep the peak current manageable for the pre-charge relay, usually under 5 amps.
Okay, let's talk about the main contactors, the accumulator isolation relays or errors, again, a COTS-only component.
Absolutely non-negotiable COTs. We specify proven, reputable brands, Gigavac T connectivity. They must be rated for a higher voltage than your system, so an 800-volt contactor for a 600-volt system.
And the most critical specification?
The ability to break under load. This means if there's an emergency, the contactor is certified to open and extinguish the massive electrical arc that forms when you try to interrupt hundreds of amps of DC current. A cheap contactor will just weld itself shut.
Now, a key safety feature the rules demand is auxiliary contacts. Why are these so important?
Because they address the primary failure mode of a contactor, welding shut. The auxiliary contacts are a separate, tiny set of low-voltage contacts that are physically linked to the main high-voltage contacts.
So they're a feedback mechanism.
A physical feedback mechanism. The VCU sends a command to the AR open, and then it reads the state of the auxiliary contacts. If the auxiliary contact says it's still closed, the VCU knows the main contacts have welded.
So you compare the command you sent with the physical reality you're getting back.
Exactly.
Yeah.
It's a critical safety check.
Yeah.
It prevents the car from thinking the HV system is safe just because a software command was sent. This detection is a top priority safety function.
That adds wiring and complexity, though. Is that a risk?
It is, but it's a calculated one. You're adding minor wiring complexity to mitigate a catastrophic failure mode. The risk of welding is a Severity 5 event major personnel risk. We accept the extra wiring and mitigate that with good harness design. The trade-off is well worth it.
Makes sense. Finally, for the PDU, Let's talk about the coils for these big relays, the economizer circuits.
Right. To close these big AIRs, you need a huge jolt of current, sometimes 3 or 4 amps, to overcome the spring. But you can't maintain that current continuously.
Why not?
The coil would just overheat and burn out, and it would be a massive drain on your 12-volt battery. So you need an economizer.
Something that drops the current to a lower hold level once the relay is closed.
Correct. We mandate a PWM, or pulse width modulation, economizer circuit. The controller hits the coil with a solid 12 volts for maybe 100 milliseconds to snap it shut, and then immediately drops to a PWM signal with a low duty cycle, maybe 20 or 30%.
Which effectively lowers the average current.
Dramatically, it drops the holding current to less than half an amp. This protects the coil and, crucially, conserves that precious low-voltage battery power during the endurance event.
Okay, section 3. Let's shift to the DC-DC converter, the low-voltage powerhouse. What are the main things this is powering?
The 12-volt system is the brain and nervous system of the car. The DC-DC powers the main vehicle control unit, the VCU, the BMS, all the safety logic like the IMD,
Yeah.
every sensor, every light. But the real challenge is the heavy loads.
The pumps and fans.
Cooling pumps, the radiator fans, any electronic actuators. The continuous load might be, 300 to 600 watts. But we have to design for the spikes when all of those turn on at once, which can hit 800 watts, maybe even a kilowatt for a moment.
And with that kind of load, let's just reaffirm the make versus buy decision. Why is it absolutely buy for the DC-DC?
Because building a reliable, efficient, high-voltage DC-DC converter is incredibly difficult. You're dealing with high-frequency magnetics, complex thermal management, and the silent killer. Yeah. Electromagnetic compatibility, or EMC.
So a badly designed DC-DC can basically jam every other electronic system on the car.
It can render your entire sensor suite useless and cause an instant scrutineering failure. The risk is just too high. COTS solutions from reputable companies have already solved these problems.
So what are the top COTS recommendations?
There are really two strategic paths. For the absolute highest power density and lowest weight, top teams use Vickers modules. Their efficiency is incredible, over 93%, and they're tiny, but they're very demanding. You have to follow their thermal and EMI design guides to the letter.
And the other path?
A more rugged, industrial approach, like modules from TDK Lambda. They're bigger, they're heavier, but they're also more tolerant of, let's say, a less-than-perfect integration. For a first-year team, that robustness can be a lifesaver.
Let's talk about the cutting-edge wide bandgap semiconductors, SiCe and GaN. How are they changing the game here?
They're a revolution. They let us crank up the switching frequency to incredible speeds, way past 500 kilohertz, sometimes up to a megahertz.
And why is that so important?
Because traditional silicon MOSFETs have high losses when you switch them that fast. Silicon carbide SiC and gallium nitride GaN have drastically lower switching losses.
And higher frequency means you can use smaller inductors and transformers.
Exactly. The size of your magnetic components is inversely proportional to the frequency. So by doubling the frequency, you can roughly halve the size and weight of the heaviest parts of your converter. This is how we hit our aggressive weight target of under 1.2 kilos for the whole unit.
And what topologies are the top teams using to take advantage of these new materials?
They're favoring resonant converters, specifically the LLC resonant converter or the phase shift full bridge. The reason is that these topologies allow for zero-voltage switching, or ZVS.
Which means you're switching the transistor when there's no voltage across it, minimizing losses.
Precisely. This is how they push efficiencies above 97.5%. And remember, every watt you don't waste as heat is a watt you don't have to manage with your cooling system. Better efficiency leads directly to a lighter car.
It's a virtuous cycle. Let's lock in the key specs for the SOR.
Okay. First, input voltage range has to be wide. From 300 volts at the bottom of the battery pack all the way up to 700 volts to handle regenerative braking spikes. A stable 13.8 or 14.5 volts. Power. 800 watts continuous is the target. But here's the crucial spec. It must handle a 100 amp peak current for at least 30 seconds.
Why so specific?
That's to handle the inrush current when all the cooling fans kick on at once. If the DC-DC can't supply that peak, the 12-volt bus will sag, your VCU will reboot, and your car will stop dead on the track.
And the final critical safety spec, overvoltage protection.
OVP. This is non-negotiable.
Yeah.
If the DC-DC's control loop fails, it could dump hundreds of volts onto your 12-volt system and instantly fry every piece of electronics in the car.
A catastrophic failure.
Total loss. So the DC-DC must have built-in OVP that will shut it down if the output ever exceeds 16 volts. And strategically, we often add a second external crowbar circuit as a redundant safety measure. It's a sacrificial circuit that shorts the output to save everything else.
Moving to section 4, the OBC, the onboard charger. This often feels like an accessory, but you say it's a tactical tool.
It absolutely is. In FSE, the time between events can be incredibly short. A slow, unreliable charger can mean you literally miss your track time. Charging reliability is operational agility.
So what's the standard component we're mandating?
To stick with our COTS reliability strategy, we recommend the Elcon HKMF series, also known as the TC charger. It's basically the de facto standard in FSE. It's IP67, rugged, and most importantly, it's CAN controllable.
So the battery management system, the BMS, can talk to it and control the charge.
The BMS must be in total control. Now, the charger also has to be a good citizen on the electrical grid at the event. This brings us to power factor correction, or PFC.
You can't just plug in a dirty load that messes up the power for everyone else.
Yeah, exactly. The event organizers enforce strict grid standards, so we mandate active PFC to ensure the charger has a power factor over 0.99. Top teams do this with advanced designs like an interleaved totem pole PFC, usually using GaN transistors to get the highest efficiency and cleanest power draw.
Let's talk about that CAN communication, the digital handshake between the charger and the BMS.
This is a critical safety loop. It runs over isolated CAN, usually at 500 kilobits or 1 megabit per second in a modern car.
And what's the key safety protocol that has to run on that CAN bus?
The safety heartbeat. The BMS has to constantly send a message to the charger, maybe once every second, saying, "I'm okay, the battery's okay, here are the current and voltage limits."
And if the charger stops hearing that heartbeat,
It has to assume a fault. We specify a maximum 5-second timeout. If the OBC doesn't get a valid message from the BMS in that window, it must immediately and automatically shut down the charge.
that prevents a BMS failure from leading to a dangerous overcharge situation.
Correct. It's a fundamental safety interlock.
And what about the physical interlocks on the charge port itself?
Two critical ones.
Yeah.
First, vehicle immobilization. When you plug in the charge cable, a switch in the port must physically break the shutdown circuit. This makes it impossible for the car to enter ready-to-drive mode while it's plugged in.
And the second one prevents hot plugging.
Yes. We mandate charge plugs that have the high-voltage interlock loop, the HVIL, integrated into the connector itself. The design ensures that if someone tries to yank the plug out while it's charging,
The HVIL pins disconnect first.
the HVIL breaks first. That immediately opens the main ARs, cutting the high voltage before the main power pins physically separate. This prevents a massive, dangerous electrical arc.
Okay, section 5, the neural system. HVIL, STC, and failure mitigation. This is where the scrutineers live, right?
This is their home turf. We start with the HVIL. It's a simple series circuit that runs through every single HVIL closure and connector, confirming they're all securely latched.
And the connectors themselves have to be special.
They have to be last make, first break. The HVIL pins inside the connector are shorter than the power pins. When you connect it, the power pins make contact first. When you disconnect, the HVIL pins break contact first.
Same principle as the charge port. Power is always the last thing on and the first thing off.
Always. Now, a huge mistake teams make is how they monitor the HVIL. Simply checking for 12 volts coming back through the loop is a flawed design,
Why is that? What's the fake closure problem?
because a simple wiring fault, like the HVIL wire chafing and shorting to a 12-volt source somewhere, will fool the system. The VCU will see 12 volts and think the loop is secure, even if a major battery container is wide open.
That's a massive safety breach. So what's the robust professional solution?
You have to send an encoded signal. The VCU should output a specific PWM frequency signal, say 10 kilohertz, down the HVIL wire. Then at the other end, it has to look for that exact 10 kilohertz signal coming back.
So if it just sees a steady 12 volts, it knows there's a fault in the wiring itself.
Exactly. It can distinguish between a healthy closed loop and a dangerous wiring short. It's a much more resilient and safer design.
What about a crash, specifically with in-wheel motors, if the whole wheel assembly gets torn off?
A very high severity scenario. We use what's called the shearing the wire strategy. The low current HVIL wire that goes out to the motor has to be routed so it's the weakest link. It must be designed to physically snap and break before the huge, thick power cables are pulled tight.
So you guarantee the power is cut before the main AC lines can be severed.
It's design failure to ensure a safe outcome.
Okay, the shutdown circuit, the STC itself, the logic has to be hardware, not just software.
Absolutely. The SDC must be a hardwired, normally closed circuit that directly controls the power going to the AR coils. Software can request a shutdown, but the physical break has to happen in hardware independent of any code.
And when a fault occurs, it has to be latching. What does that mean in practice?
It means the fault state persists. If the IMD trips, the system shuts down and stays down, even if the fault condition disappears for a moment. It won't just flicker on and off.
And how do you build that?
With a latching circuit. This can be a special self-latching safety relay or a simple digital flip-flop in the logic. Once the fault signal sets the latch, the only way to reset it is for a human to physically cycle the low-voltage master switch. It forces a deliberate action.
Now, for the most notorious part of safety scrutineering,
Hey.
the brake system plausibility device, or BSPD.
Ah, the BSPD, a huge stumbling block. It's there to prevent the driver from braking hard and accelerating hard at the same time. And the rule here is crystal clear and so often violated.
What's the rule?
It must be a non-programmable pure hardware device.
No microcontrollers allowed. Why so strict?
Because software adds complexity and potential for bugs. The rule makers demand that this critical safety function be immutable and transparent. So you have to build it with old-school analog comparators and discrete logic gates. You have to prove to the scrutineer that its function is locked in hardware and can't be changed by a line of code.
Fascinating. Finally, the TSAL, the Tractive System Active Light.
Simple purpose. Green light if the HV bus is below 60 volts and safe. Flashing red light if it's above 60 volts and dangerous.
And a design requirement.
Again, pure hardwire logic. A comparator that directly measures the DC link voltage. No software in the loop. And here's the strategic tip. Design the red light circuit with a resilient power source, maybe a small supercapacitor, so it keeps flashing even if the main 12-volt system dies, as long as high voltage is present.
Its job is to protect people, even if the rest of the car is dead.
That's its only job.
Okay, we have the safety foundation. Section 6 is about putting it all together. Integration, cooling, and the future. Let's start with the CDU, the Converged Design Unit.
This is the strategic goal for packaging. A 3-in-1 unit that integrates the PDU, the DC-DC, and the OBC into a single enclosure.
What's the advantage?
You share everything. One housing, one set of connectors, one shared cooling plate. Our analysis shows this approach can reduce the total volume and weight of the power electronics by over 30% compared to 3 separate boxes.
But packing all that heat together means liquid cooling is a must, right?
Absolutely mandatory. At the power densities we're targeting, air cooling just can't keep up. A 50-50 water glycol mix has 4 times the heat transfer capability of air.
And what does the housing itself need to look like?
A precision CNC machined aluminum block is the way to go. You machine complex 3D cooling channels directly into the block that run right into the hottest components, the specifications, the bus bars. The thermal spec is tight. Junction temperatures of the semiconductors must stay below 125 degrees C, even in 50 degrees C ambient temperatures.
Hot summer race days.
Exactly. This is how you prevent thermal shutdowns during the endurance event.
And packing everything so tightly brings back the silent killer EMI.
It does. The high switching speeds of CD and GAN create a ton of high-frequency noise. The mitigation strategy is to make the entire CDU a perfect Faraday cage.
How do we do that?
On the PCB, you minimize your power loop areas to act less like an antenna. The aluminum casing itself needs to have perfect electrical continuity at every seam using EMI gaskets. And critically, any HV cable shield must have a 360-degree connection to the enclosure with a proper grounding clamp. No pigtails.
Now for the really exciting part, the e-fuse revolution. Why are we moving away from old-school mechanical fuses?
Because they're slow, dumb, and single-use. They work on a simple thermal principle. An intelligent e-fuse from a company like TI is a semiconductor. It's digital. Its response time is in the microseconds, often less than 100 microseconds.
And what does that speed let you do?
It lets you protect your incredibly expensive inverter and motors from transient faults far faster than any mechanical device ever could.
And the tactical advantage during a race?
It's a game changer. Imagine a temporary fault, a current spike from hitting a big bump. A mechanical fuse blows, your race is over. 0 points. An e-fuse is software resettable. The VCU can detect the fault was transient, check that the system is stable, and then re-enable the circuit on a fraction of a second.
So a race-ending failure becomes a momentary hiccup.
Exactly. It massively improves your chances of finishing the endurance event.
All of this complex integration requires a formal safety analysis, the FMEA.
The failure mode in a FST analysis is mandatory for the electrical systems form. It forces you to think like a pessimist. We focus on the highest severity modes.
Like what?
Contactor welding, severity 5. We detect that with the auxiliary contacts. Discharge failure, also severity 5, detected by the hardwired TSAL. And a big one is DC-DC overvoltage, which can destroy all your LV electronics. We prevent that with the internal OVP and the external crowbar. Every potential failure needs a documented detection and mitigation plan.
And how do we test all this complex logic safely before it goes in the car?
You must use hardware-in-the-loop or HIL testing. We mandate setting up a test bench where you can simulate every fault, an IMD fault, a BMS fault, a BSPD trip, without a real high-voltage battery connected. You can safely verify that your SDC latching logic works perfectly under every conceivable failure scenario.
And the simple manual check.
The MEGR. You have to be routinely using an insulation resistance tester at 500 or 1,000 volts to check your TS to chassis resistance. Before every event, during the build. If that number ever drops, the car is grounded until you find the fault. It's basic, disciplined engineering.
We've covered a massive amount of ground here. Let's wrap this up with the final strategic review, the final verdict on make versus buy.
The mandate is clear. Buy the high-risk, certified safety components. You buy the DC-DC, the IMD, the charger, the contactors. This is your foundation of reliability.
And you build your competitive advantage by focusing on the make strategy.
Yes, you make and customize the integration, the PDU's mechanical design and cooling, the SDC safety logic, the entire wiring harness, which is where most failures happen, and of course the VCU software that ties it all together. That's where a team builds its unique expertise.
You've really driven home the point that it's not about raw power. What's the final word for this new team?
It all comes down to points. A reliable 40-kilowatt car that completes the endurance event is infinitely superior to a 100-kilowatt car that fails scrutineering because of a simple isolation fault. In Formula Student, reliability is king. You have to finish first to first finish.
It's performance through dependability, a whole new way of looking at it.
It is. Which brings us to a final thought for you to consider. We talked about the intelligent eFuse and its microsecond software resettable nature.
Right, turning a hard failure into a soft one.
So if a top team truly masters that technology, if they know the absolute thermal limits of their motor and inverter down to the millisecond, how might they use software to intentionally push those components past their continuous ratings, knowing that the eFuse is their safety net, ready to catch and reset a transient fault instantly?
Wow, so using a safety device as a performance enabler.
Mastering that digital safety margin, not just the physical hardware. That's the next frontier in competitive advantage. It's about data, not just horsepower.
That is a high-risk, high-reward strategy built entirely on the foundation of reliability we've just discussed. A fascinating place to end. Thank you for walking us through this.
My pleasure.
Thank you for joining us on the Deep Dive. We'll see you next time.